Okay, so welcome everyone. So welcome to our workshop on zero-cost deep learning for microscopy. My name is Guillaume Jacquemet, so I will be one of the tutors today. And then with us, we will also have Lucas, who is actually already here. And then a little bit later on today, we will have Romain and Ricardo that will be joining us as well for the workshop. So Romain and Ricardo are running another workshop for the I2K conference, and then that's actually running now. So he will be finishing in a couple of hours, but they will be joining us afterwards. So I just thought that since we can't meet in person, unfortunately, I will just introduce ourselves a little bit. So maybe Lucas, you can say a couple of words about yourself, and then I can introduce everyone else afterwards.
Hi, everyone. Thanks for coming. It's great to see so many people again. I'm Lucas from Chamier. I'm a PhD student in the Henriques lab. And yeah, zero cost is basically the main part of my project. So we spend a lot of work building it, and I hope you like it and find it easy to use it. Yeah.
Okay, thanks, Lucas. And then with us later, so there will be Romain, who is also one of the key contributors for the zero-cost platform. So he is currently a postdoc with Ricardo Henriques. Ricardo and his lab have been working with my lab together to work on this project. So he will also introduce himself later on if you don't know him already. And then myself, so I'm a group leader in Åbo Academy, which is a very small university located in Turku in Finland. Which is a very small city that you've probably never heard of before. But actually the zero-cost project has been involving many other people, so it really takes a village to build a tool. Many people have contributed in terms of either providing codes or testing the platform or providing data. And actually we have with us as well Christophe Leterrier, who is also one of the contributors to the platform. So thanks, Christophe, for joining us, and thanks for providing some of your really cool data so that we can test out the platform. Since we also can't meet in person, then I thought it would be nice for you to see sort of where we are calling you from. So as I said, so I'm calling you from today.
Guillaume, yeah. There's something blocking part of the presentation. Can you maybe remove that? Yeah, that window that you just moved it.
This one?
Yeah.
Oh, okay. Let me see if I better.
Can still see it.
Can you see it at the bottom here?
No, now it's gone.
Now it's gone.
Okay, good, awesome, thanks. So I'm calling from Finland. Lucas and Romain are located in London, and Ricardo just moved to Lisbon in Portugal. And we've actually never met in person. So it's a kind of a fun project that started on Twitter. Okay, so here is kind of the outline of the workshop. So feel free to stop me if you have any burning questions or if something is not working properly, because now I can't see you anymore. So I'm just talking to my computer screen. So don't hesitate to interrupt me. But we will start with kind of a general introduction talk that I will be giving. And then after that, we will take a short break, and then you will have a chance to kind of introduce yourself and tell us a little bit about why you are interested in using deep learning for your work. And if you've not done it already, then please add a slide to the Google slide presentation. So you can find the link, hopefully, in the chat for the Zoom. If not, then Lucas maybe can add it, or you can also find it on the Slack channel. And then after that, we will kind of get on with the practical work, so we can show you on how to use the platform. And here is a kind of a brief outline of the talk. So we will start discussing a little bit about deep learning for image analysis and what can you actually use it for. Then we will go over very simplistically how does it work. And then I will highlight kind of some of the key features of the zero-cost platform. Okay, so let's get started. So why do we want to use deep learning to do image analysis? And I think the idea behind this is really to try to train the computer to analyze images in the same way than the human brain work. And by that, I mean is that if you just look at this image, in a few seconds, your eyes and your brain behind it will have been able to identify patterns. You will see that there's a lot of objects that are round, that have a specific colors, and you know that those objects are very similar to each other. So even so, you would not have any idea of what there is in this image. So if you have absolutely no biology background, you will not be able to recognize red blood cells here in this image. Your eyes have been trained to identify objects and patterns from your birth. You will also be able to identify here that you have something else in the middle that has a different shape and different colors. But if you do traditional image analysis just based on intensity, then it's actually quite difficult to train a computer or to write a computer algorithm to distinguish between those objects, because there's not a lot of difference in terms of colors, and many of those objects are overlapping. However, now there is computer algorithms that you can train to kind of behave a little bit in the same way as your brain does, in order to kind of identify those patterns. And that's really kind of the aim behind computer vision, is to try to make use of these tools to analyze images. But what can you actually use it for? So actually, in the recent years, it's really been an explosion of new methods and paper describing these methods on how deep learning can be used to analyze microscopy data. And here is just a small subset of them. And deep learning methods really uncover almost anything you can think of in terms of microscopy image analysis, from object detection and segmentation, image registration, restoration of images and denoising, improvement in resolution and super resolution, as well as labeling. And so I will show you an example of some of those on some of the things you can do using the ZeroCost platform. So if we start with image segmentation, so I'm assuming you're familiar at least with some basics of image analysis, and you will know that image segmentation is a strategy that you will use to basically identify structure on your image and create a mask out of it. So here is a classical example of how you will segment an electron microscopy image, and here we wanted to segment the plasma membrane in these electron microscopy images. So here is the kind of image that you would have, and here is a segmentation target where the outline of the cells here have been identified. And then here, basically using a deep learning algorithm called UNet, you can train a computer algorithm by providing those images, how to segment those images automatically. So here, for instance, is some data that we obtained using the ZeroCost platform, where by training a UNet models, and we were able to segment quite nicely those plasma membrane here in the electron microscopy images. And UNet can also work for 3D images. So here is an example of a 3D electron microscopy data, and we wanted to segment the mitochondria. So here is mitochondria, and here are the prediction from the deep learning network. So once you've trained the deep learning network to do what you want it to do, then it can generate high quality segmentation data. So from, of course, electron microscopy data, but you can also apply it to fluorescent microscopy data. Another example of segmentation would be, for instance, segmenting cellular structures such as nuclei. So for that, in ZeroCost, we've implemented StarDist, which is specializing in segmenting rounded, oval-shaped structures like nuclei. So the video will play again. And here, for instance, we have migration data of cancer cell migrating, and we've used StarDist to automatically detect the nuclei and to track them. So we can combine, of course, segmentation with other image analysis, such as segmentation, such as tracking, sorry. So here, for instance, so if you're interested in automated tracking, then we've used and combined StarDist and Jacquemet together, and I would be happy to discuss that further during the workshop or afterwards, if that's something you are interested in. So just some example of segmentation. One of the big things that you can do with deep learning is object detection. So object detection is a little bit like segmentation, except that you're not generating a mask afterwards. Instead, you are generating bounding boxes. So there's a deep learning algorithm is identifying object and structure in your images and telling you where they are. So a very classical example would be a self-driving car. So for instance, here is a video from a Tesla car while it's driving. And because the car needs to kind of be able to identify what's going on the roads so that it can not crash. And then it's using object detection algorithm to detect other cars and as well as pedestrian. But of course, you can use similar technologies to identify cellular states or objects in your microscopy images. So here, for instance, we trained a deep learning algorithm called YOLO to identify cellular states. So here, cells that are migrating and the different shapes, or if they are dividing. So we train YOLO to identify the cellular states, and then we can apply them to live cell migration movies. So here are output of the YOLO deep learning networks that is identifying those cells and then classifies them in function of their shape and cellular behavior. So as another example of other kind of image analysis you can use deep learning for. Of course, something else that especially we are very interested in the lab is denoising and improving the images. And so why are we so interested in denoising is, especially if you are interested in live cell imaging, then you will know that lasers are very toxic for cells. So you probably want to use as low laser power as possible when you're imaging them. If you're doing fluorescent microscopy, you will know that you will also need to overexpress fluorescent protein to be able to observe them or to tag the endogenous molecules, which means that if you do the overexpression, you want to have a very low endogenous expression so that you don't get any artifact due to overexpression, which means that when you combine those two things together, you end up with noisy images. So there's a really need for improving the quality of those noisy images. And that's somewhere where deep learning can really be useful as well. So for instance, a deep learning network called CARE can be used to really improve the quality of your microscopy images. And here we've used CARE to improve the quality of structural elimination microscopy data. And it's especially useful for SIM because SIM still require quite high laser power to be used. So it's really nice if we can tone down those lasers. We get noisy data, but then we can use deep learning to improve the quality afterwards. Another network that is available in ZeroCost is one called noise to void. And here is an example on how we use noise to void to improve the quality of noisy data. And so we will show you how to use noise to void today in the workshop. If you're interested in super resolution microscopy, so we've also implemented a network called DeepStorm, which allows you to reconstruct densely packed single molecule localization microscopy data. So those data are actually microscopy data from Christophe Leterrier with us today. So thanks, Christophe, for providing us with really beautiful SMLM data, as always. And then the final task that I want to kind of highlight that you can use deep learning for is image labeling. And by that, I mean is to artificially label your image. So let's say you have a picture of an actin staining here, and then you would like to predict from this actin staining where the nuclei will be in your images. And then for that, we can train different deep learning network to generate fake images of what a different label would look like in these images. So here we've trained pix2pix to translate an actin staining into a DNA staining in order to predict where the nuclei would be in the image. So here is a ground truth, so that's a real image, and then here is an image generated by pix2pix predicting where the nuclei will be from the actin staining, and here's a comparison. And you can see that this deep learning networks is doing a pretty good job as to identify where the nuclei will be and generate a very realistic image from a different label. So you can use this kind of technology to maybe multiplex or to facilitate downstream analysis. So for instance, here we've used this kind of prediction to generate from actin live cell imaging data prediction where the nuclei will be, so that we can then threshold them in order to do automated tracking. So doing automated tracking from this kind of actin movies is really difficult because identifying where single cells are is quite challenging. But as soon as you know where the nuclei are, then the automated tracking is now much, much easier. So by predicting where the nuclei are from the actin movies, when we can do automated tracking using this kind of data. Okay, so I went quite fast, but hopefully this kind of gives you a nice overview of some of the deep learning networks that are available in ZeroCost, but also the kind of data analysis you can do using deep learning. Of course, there are many other types of deep learning algorithm available out there, but I think here it's kind of give you a good overview of what's possible. But now, how does it work? So if we compare deep learning algorithm compared to classical algorithm, so when you do typically image analysis, then you will have an image. So here you have an image of nuclei that have been labeled. So you have fluorescent nuclei, and you have many of them in the same image. Classically, if you want to threshold those nuclei, so if you want to do segmentation, then you will apply a formula to find them. By that, I mean you will probably do a little bit of filtering to try to remove the noise, and then you will do an intensity-based thresholding to identify the bright pixels. And then that formula altogether will be applied to the rest of your images to do the segmentation. But actually, a deep learning algorithm works, or at least a pipeline works in a quite different way. So first, you need to train the deep learning algorithm to do what you want it to do. And to do that, you need to provide it images of the nuclei as well as images of the output that you will want it to generate. So first, when you want to use deep learning, very often you will need to generate a training data set. And that training data set is, of course, very important because it will dictate on what kind of task your deep learning will be doing. So here, to do the image segmentation or the nuclei segmentation, you give it images of nuclei as well as the corresponding mask, so that the network can start to understand what kind of task you want it to do. And then once you've trained your deep learning algorithm and that it knows what it's supposed to do, then you can use that model that you've generated to basically just do the task you wanted to do. So there, once the training is done, you have a model, and then you apply that model to your images. So it's really a two-step process when you want to use this kind of technology for your images, which means that it's important to know two things. So the first one is how to train deep learning algorithm. And then if you are using model trained by others, how they've been trained so that you can really understand what kind of tasks they are able to do. But if we want to kind of go in a little bit more details on what a neural network do, so a very simplistic way of looking at it is that a deep learning network is composed of multiple layers, and each layers has tens to hundreds of filters, and each of those filters will apply basically an image processing step. And each filter is defined by tens to adjustable parameters. So the same way as you would have when you do a classical image analysis, when you apply a filter, you have ways of tuning it. And those parameters are often called weights. And if you put the whole network together, then you have a network that can be defined by tens to hundreds of filters that are defined by tens of, or that can be modified by tens of parameters, which can lead you to up to millions of different adjustable weights. So basically, you have here a system where you can adjust a lot of different parameters that's going to affect how your image is going to be processed through the pipeline. So it's a very simplistic way of looking at it, but hopefully it helps you understand a little bit on how it works inside. And the reason why deep learning is so powerful is because during the training step, the network is able to learn on how to transform your source image into what you want it to achieve. So here is an example of denoising. So we want to denoise noisy images here of the mitochondria into something that looks a little bit more like this. And as the image goes through the network is able to learn on how to improve it. And how does it do that? Well, first, when you start the training, all those weights and parameters I was describing before are initialized randomly. So the first time your image go through the whole pipeline, you get an image which is completely ridiculous and doesn't actually mean anything. But what the network does is that it compares that image to what you want to achieve, and is going to score on how well they match. And if they don't match well at all, then you get, of course, a poor score. Because deep learning training is a really iterative process, you need to repeat it many, many times. What happens is that the scores that you get here will make it, it will change what kind of parameter you have inside of the model in order to reduce the difference between your output and your expected result. And for that, you use a formula called back propagation, which is here, where basically the weights, so the parameters used at the different filters are changed in a way so that the errors between those two images here is minimized. And then it's really an iterative process where by training again the network, by going through this process, you can slowly improve the quality of your final images in a way that it matches what you want it to do. So there again, it's highlighting really the importance of the training data set that you will use to train the deep learning network, because the network is really learning on to the task, which is to generate what you want it to generate, which is based on the training data set. So that's kind of a brief overview of the theory, but what actually happened in practice? So if you wanted to start training your deep learning network, what do you need to do? Well, it all starts with the training data. So the first things that you need to consider is the training data set. And there's really two different ways a training data set can be created. That really depends on the type of deep learning network you're going to use and how they will learn. The first one is called supervised training, and it's mostly what I've been describing so far, where you need to have a training data sets which are pair of images of input and expected output. So training source and training targets. So here are images. We want to transform the actin staining into a nuclei staining of images, and then we provide matching images of those two, the same field of view for the two labels. If you wanted to do denoising, then you will provide a low quality images that's very noisy and the same field of view, which is high quality denoised image. So that the training data set is very specific. You need matching images. And most deep learning networks that you will find in zero cost use this supervised training approach. But there is another training approach that can also be used in other deep learning networks, which is called self-supervised. And then there, the training data set doesn't need matching images anymore to train. So that's the case, for instance, noise to voice and CycleGAN, where, for instance, in CycleGAN, the network can learn how to transform one image into another without matching pairs. And there, the architecture of the network is a little bit more complicated. But so the reason why I'm spending a little bit of time here to highlight is really each network has specific data requirement to train. So a type of training, as I was highlighting, but also in terms of image formats, how do they need to be labeled, and so on. So before you start using zero cost, and actually it's true as well for any kind of deep learning that you want to do, one of the first things you need to do is what kind of training data sets you need and how to generate it. So we put quite a lot of information in our wiki page on giving advice on how to generate those training data sets. For the zero cost platform also, and you will see that later on in the workshop, each notebook contains a lot of information on what kind of data is expected to be used for the training. So check those out before you start generating your own data. Once you have a training data set, and you will see that as well during the workshop today, the first thing that actually happens is that your training data set, it splits into two categories. The first one is the actual training data that the network will use for learning, and the second part is the validation data. And generally speaking, about 10% of your training data set need to be transformed into validation data. So that's something good to keep in mind, because depending on how much images you have, you will not be able to use all of it to actually train the network. So at the exception of noise to void, you will not be able to train a deep learning network with only one image, because very often you will need at least two images, one for the training and one for the validation. And then, so the network will then learn from the training. So in the process I was describing, so you have the training data set and the network learn from the training. And I was explaining before, so the training is really an iterative process. And one round of training is called one epoch. And a deep learning model is generated at the end of each epoch. So once the network has seen all your images and it thinks it has an idea on how to transform them, then it's done it once, then you have one model. And at the end of each model is checking on how well the model behaves. But of course, depending on the size of your training data sets, the model is not necessarily able, the network is not necessarily able to look at all your images at once, and epochs are generally divided into steps. And the steps is also parameters that you will find in the notebook later on in the training, and that's defined by the batch size. So the batch size basically dictate on how many images at once can your deep learning network analyze, and that depends on your computing power. So if you have a very powerful GPU, so graphic cards to do the training, then you will have to have you will need to be able to have a bigger batch size. But if you are limited in resources, then you will need to use a smaller batch size. So analyze less images at once, and then the training will have more steps and it will take more time. But at the end of each epoch, so an epoch again is one round of training, the model will score on how well it's performing. And then you will get something that's called the training loss. But also at the end of each epoch, now the model will look at your validation data. So it's not look at your validation before, and it's not learn at all from it. And using the validation data, the model will be able to assess how well it's performing on something that is not learned from. So some new data that is not seen before. So that's a really useful way by which deep learning can also score how well the model can generalize on data that's a little bit different from what is being used for training. And here you will also get another score, which is called the validation loss. So once again, so this score will tell you how well the model perform on your validation data. So why is that important? Is because one of the first outputs that you get after training a deep learning model is this kind of graphs here, which is a representation of the training loss and the validation loss over the number of epoch that you've used to do the training. And you will see here, so the training loss is going down progressively, which means that there's less and less errors. So your model is able to learn from the training data, which is great. But you also have the validation loss, which is also going down and showing that your model is also able to generalize to the validation data, which means that the things that is learned from the training data set can now be applied to your validation data to improve them or to do the segmentation you wanted to do. However, so that's the case when things go well, but if the training goes wrong, then you might see something like this. So where the training loss is going down, so the model is still able to learn from the training data. However, now the validation loss is going up, which means that even so your model is learning from the training, it's not able to learn or to apply what is learned to improve the result of your validation. So what does it mean is that either your training data set is too small and is not able to generalize to your validation data set. And that basically indicates that your model is probably not going to perform too well on data that is not exactly the one that you've used for the training, which makes it maybe not as useful. So you will see that again during the workshop. But of course, the things that you, of course, strive for is to have a model. And then once you have this model, then you can just apply it to new data. Here, the thing that's really important, of course, to realize is that training is a really slow process and require a lot of resources, and it can take hours to days to get a good deep learning model, but the prediction takes seconds to minutes. So it's a really fast process. So it's hard work to get the model, but once you have the model, then you can hopefully generate a lot of data using it. But of course, training is the most important part because that's really dictating on how well your model is going to behave. So here is one example of this, where we are trying to denoise actin images using CARE, which is one of the denoising network I was mentioning earlier. And here is an example of noisy images. And here is a ground truth image for this field of view. And then if we generate a model using actin images here, then you can see that we can restore those noisy images quite nicely. And then we can recover some structures information here from the noisy data. However, if we now use a model trained on something that's different, let's say mitochondria images, which has nothing to do with the actin labels that we want to rescue here, then actually, if you look at it from afar, it might look like you've denoised the images, it might look a little bit better. But as soon as you start to zoom in, you can see that now you've completely lost and your image is completely modal. So really highlighting the importance here to train data in order to train a model to do what you want it to do, which is here denoise a specific type of structures. Another example here now for segmentation. So we want to train here a segmentation model to identify nuclei in those images using StarDist. So here's the kind of raw data that we start from. Here's the kind of masks that we want to achieve. So StarDist is an amazing tool to do nuclear segmentation, and there are some excellent models already available. So of course, it makes absolute sense to use those models. But what happens if you use a pre-trained model on those data? Then you can see that your nuclei are nicely segmented, which is great. That's what you want. However, the model is also failing here in some area of the images. You get large cal artifact at the top. So that's, of course, not ideal. That's probably not what you want. So what you can do then is train your own StarDist network so that you can get the best data possible using your own data. So here, there's two things that are really important to highlight is that the data sets used to train the deep learning network is almost one of the most important things to know about. But also always validate the models that you're using, whether they're the ones that you're making yourself or models that you are using from someone else, using ground truth data to make sure that you're getting the best results possible and no artifacts in your images. So I think I've highlighted side quite a lot. So it's important to train your own, or it at least very useful to be able to train your own neuronal network with your own data. And how can you do that? Well, very often you will need to install, of course, the required software, which can actually be surprisingly hard, especially when you need to start battling with graphic card dependencies, TensorFlow and CUDA. And then depending on what kind of neural network you want to use, they don't necessarily have the same requirements, which make it even more difficult. You will need to adapt the code. Often it's in Python. So maybe many of you are comfortable with this, but of course, it's not the case for everyone. So that's make it challenging. And also, you might not just have the time to do that. And very often, you will also need access to powerful workstation to be able to do the training. So it kind of feel, especially when I started using deep learning to analyze my images for my lab. So I have a strong biology background. So it felt a little bit like this, trying to kind of operate the International Space Station. So that's why with Ricardo's lab, we've decided to work on a platform called ZeroCost Deep Learning for Microscopy to try to make it as easy as possible for people like me to use deep learning. And what do you need? So you need a computer. You need, of course, data that you want to analyze and training data. And then you need a Google account at the moment, and you will store your data to Google Drive. And ZeroCost, we provide notebooks that you will see later on today. And then basically Google Drive and the notebook we provide can communicate with a platform called Google Colab, which allows you to train deep learning network for free. Google Colab provides all the computational powers that you need for that. And then you will also be able to do the prediction directly in the cloud. You can, of course, download the results and then do further analysis later on your computer. So what you get out of ZeroCost is that you get a free cloud-based access to GPU, which allows you to train the deep learning networks. There is a very simple user interface, so we will go through that. And there's no coding skill required. You can, of course, adapt it if that's what you want. And it's also a single platform for the training, the prediction, and the quality control of deep learning algorithm. And in our opinion, quality control is actually one of the really important parts here, so that you can make sure that the model you are using will be of adequate quality. So here is kind of a screenshot of what the platform looks like, but again, you will see that soon. So the first thing I want to highlight about the ZeroCost platform is the quality control. And for that, you will need to use some extra data, so maybe some training data that you're not using for the training, and you will be able to compare basically your model prediction to ground truth data. And in this case, it's very important to use images that have not been used to train the network, so you can really assess the quality of the prediction that your model is generating. And so you will see again, so in the ZeroCost notebook, depending on what kind of task you want to do, then we've included metrics to assess the quality of the predictions that kind of match what you want to do. So here, for instance, was an example for denoising, and then we've implemented things like SSIM to assess the similarity between your prediction and the ground truth data. In the case of segmentation, you will see something like this, where you can compare the target mask to the prediction mask and get metric scores such as E over U, so intersection over union, or F1 score. So if you're interested about those metrics, we describe them quite a lot in our wiki and in the ZeroCost paper, but I'm also happy to discuss that later on. Another very important part of the ZeroCost platform is that there is a unified structures in all the ZeroCost notebook. And by that, I mean that when you learn how to use one, you should be able to use any of the others. Of course, the data requirement to train the deep learning network will be different, but the notebook itself are identical. Everything is the same in terms of the name of the parameters, the layout, and the steps is the same. And that kind of follow up the deep learning pipeline. So you will see the first steps here in green, which will be setting up the session and installs all the required software that you need, and you can do that in a few minutes. Then you can choose the path and the parameters that you want to use to train your network, and then actually train the network. And then once this is done, then you can evaluate how well the model you've generated perform. And then there's a final part where you can directly use the model if you want to there to generate prediction. I also want to highlight that many of the models that we generate can be downloaded and used in Fiji to make the prediction directly in Fiji, which might be a little bit more easier to do in some cases. But there are two other things that I want to highlight before I stop this talk. So one of the things that you can also do in the ZeroCost notebook is data augmentation. So data augmentation will happen before you start the training, and it's a way to artificially increase the training size of your data set. And what do I mean by that is that you realize by now that the training data set is the most important thing that you need to worry about when you do deep learning. And especially if you do segmentation task, generating this training data set can be really time consuming because it will often require you to manually annotate those data. So it kind of really help if you have strategy to increase the size and decrease the amount of data you need to annotate. And one common way to do this is to apply very simple image manipulation strategy, such as rotation and flip. So you can see here, so if you start from one raw images and then you rotate it and flip it, you can already increase the size of your data set by 8. And as far as a deep learning network is concerned, all of those images are, of course, related, but they are different enough that those networks can learn new things using those images. So that might really improve the quality of your model. So here's an example for YOLO, where we show that if you increase your dataset size using augmentation, then you can get much better predictions. So here YOLO is looking at cellular states using bounding boxes. And then finally, the last feature that I want to highlight is transfer learning. So I went over that a little bit fast earlier, but once you start training a network, one of the first things that you do is that you initialize the weights of all the parameters within the different layers of the model. And very often, the first thing that you do is you initialize them randomly. So when you start training, you start from a random blank model. But of course, you don't need to do that. So if you have a model that's already working quite nicely for your data, but it's not perfect and you want to improve it, what you can do instead is that instead of starting from a blank model where everything is random, you could start from the weight of the model that works okay, and then continue training on this with your own data to make it even better. So here is an example for Stardist. Here in the top image is a pre-trained model that we've used for the transfer learning. So that's a model that's already available in the Stardist Fiji plugin. And you can see that it's performing well. The issue here is we still have those artifacts at the top. However, if we use that as a starting point for our training, then we can, in a very short training session, so only in 5 epoch, we can get really good segmentation results. So by just reusing this model as a starting point for the training with our own data, then we can achieve really amazing performance in terms of segmentation. And if we were going to train Stardist from scratch using the same data set, it will take up to 200 epochs. So that's about 3 hours of training to achieve the same results. So transfer learning can really speed up the training transfer. And so transfer learning is also available in the ZeroCost platform. So I've already mentioned this, but I want to highlight this again. So many of the models that you will be able to train in ZeroCost can also be used in Fiji. So that's the case for the CSB deep learning networks such as CARE, Denoising, and Noise2Void using the CSB deep plugins. Stardist 2D can be used in the Stardist plugin, and then UNet 2D and DeepStorm model can be used via DeepImageJ. And ST from the DeepImageJ team has been helping us with implementing DeepImageJ within ZeroCost. To access ZeroCost, you can do that via our wiki page, and we will show you how to do that later on in the workshop. And finally, I also want to say that if you are interested in contributing to ZeroCost, then we welcome any contribution from the research community. So just check out our guidelines and don't hesitate to be in touch with us. We will be happy to discuss things further with you. So again, I would like to thank everyone involved in the ZeroCost project. So of course, Ricardo Henriques' groups, Lucas and Romain, but also everyone else that has contributed one way or another to the project. So on that, I'm going to stop now with this introduction. I hope that you found some of the things I've shown you interesting, and I will be happy to take any question.
Welcome to the hands-on tutorial on ZeroCostDL4Mic. I've missed some of your presentations. I've had to join late due to a prior workshop. So I've missed some of your applications. So feel free to well, mention what you're doing when you ask questions or whatever you feel is relevant. And importantly, feel free to ask questions, anything, however tangential you think that might be in during what I'm currently doing. I have a couple of things in mind that I want to introduce you to, but this is about making this time, those couple of hours, useful for you to be able to use it in the future. So whatever comes to your mind that you think, okay, but I don't understand this, just unmute yourself and talk to me. It's no problem. And if you're wondering, someone else is probably wondering as well. So bottom line is, although I've got something planned, I'm more than happy to deviate around to get to what's most useful for you guys. Okay. So
and so sorry, Romain, I'm going to interrupt you already.
Yes,
so and
absolutely.
I will also say that feel free to also ask a question in the chat box or on the Slack channels. So I will be kind of keeping an eye on those. So if you have questions you want to ask as well on the sides, then I'm happy to help there as well while Romain is doing the first part of the workshop.
Cool. Yeah. Thanks a lot, Guillaume. Awesome. So you guys hopefully have had the time to download the data that we've suggested for you to download, and that you also had the time to re-upload them onto your Google Drive. Okay. I'm showing you here a page of my Google Drive where the data is currently copied. You can see that it's exactly what we've suggested you to download and use. That's what we'll be playing with today. But I've also got a copy, a local copy right here onto my desktop so that we can take a quick look at the data first. If you haven't had the time to do this, I suggest that you do that immediately because that can take a little bit of time to download and re-upload. We'll be running this hands-on session onto two specific notebooks, two specific neural networks, one of which is called noise to void, which, as Guillaume showed you, is a denoising network. So that allows to improve the signal to noise ratio of your data. And a second one, which is Stardist, which is an image segmentation deep learning pipeline that will typically be able to, that is optimized to detect round and oval shapes. So that's really useful for nuclei, for instance, but also for round cells and anything that may be around in any type of images. But we'll be showing you how this works on fluorescence microscopy nuclear data set. Okay, so let's do. I would like us to just take a couple of minutes to look at the data that we've got right here. Okay. And because I think that's really important to understand the makeup of training data in the case of deep learning. What we've provided here, and this is what every single deep learning approaches will require you to provide to start with, is a training data set. Okay, everything in deep learning, or most things, are determined by the training data set. Crap in, crap out, good stuff in, good stuff out. Okay, so in terms of start this data set, we've actually provided a set of training images. So I'm in the start this data set folder, a set of training images right here, and the other folder right here is the equivalent masks images. Okay, let's take a quick look together at how this looks like. Here it is. We've got the image. Those are the raw data image that we'll be using for training, and they should be representative of the kind of data that you're interested in processing further down the line. And if I select also the first data set from the second, from the mask folder, you have the equivalent mask image of the same image, essentially, right? And so if I zoom in onto some parts of that data and some part of that data, what you can see is we now have identified in this mask data set each individual nuclei as an individual object. Okay, and here that's been color coded, but the underlying data is simply a number. The background is 0, and each one of those nuclei objects are number coded. And if you look in the bottom bar of the image J bar up there, you see its value is 38. This particular object is number coded by the number 38. And so that's really useful because then you can start going through all of the individual objects and to have information about each individual nuclei. This particular kind of data is so-called instance segmentation. What this means is that each individual object is segmented separately as a separate object. And so, as I said, it's really useful because you can actually isolate very easily each individual object afterwards. Okay. There's another case of so-called pixel segmentation, which is what you've seen for UNet, for instance, which will, to a large extent, only segment between background and foreground. So, for instance, in EM images, segmenting membrane, for instance. Okay, but what's really important in what I'm showing you today is we already provide, and that's the starting point, a set of ground truth data. Okay, where we're starting from, the input, and the output, where we want to get to, what we call the target. Okay, and so that's really important because that is providing that ground truth is what the network will leverage to be able to learn how to improve its own parameters to perform the task that's at stake today. Okay, so this is the burden of the user. This should be clear. Providing a training data set that is efficient and relevant is the burden of the user. And that's that will basically become the bottleneck for all deep learning methodology. What we provide through this platform is essentially a way to make all the rest of it really easy. But that first step of generating a training data that is of good quality is typically the burden of the users. We've also provided a couple of, as Guillaume just highlighted earlier, a couple of hints of things that we've learned along the way by playing with all of those notebooks, ways to kind of make the curation and generation of training data set more efficient, easier, less time consuming. So we've started also building tools around this, and we can talk about this at some point if you guys want. And actually, Guillaume will show you a way to do this for Stardist a little bit later on. Another thing that's important to talk about in the data that we have provided is we've also set aside, as part of that pre-curated data, and for which we have the ground truth, a bit of data set. So what we call test data set right here, test images and equivalent test mask, where we've set aside completely, and the neural network will never see that during training. That's never provided during training, and we'll be able to use this for quality control. So you can imagine intuitively having data for which you have the ground truth and to which you can compare the network outputs can be really, really powerful to check whether it's done a sensible thing and to convince ourselves that the performance of the network is acceptable. Okay, and again, in our pipeline, we've also integrated a quality control step that can quantitatively and qualitatively help you assess those components, those aspects. Okay, so just because of the way, sorry, are there any questions on this? Do you guys want, is that clear?
I do have kind of a question.
Yeah, of course. Fire up.
You explained the difference between the pixel type classification and the object classification. I'm familiar with the pixel kind one. In here, you have an annotation or a ground truth in which each object kind of gets its own class. Mm-hmm. How is that resolved in the between the different images, and how does that work in the deep learning consensus? Because I can imagine that you can say, okay, I want this to be number one and this to be number two, but that doesn't fit between images, right? The number one class isn't the same thing in each image.
Yeah, the absolute, so that numbering of the individual objects only happens afterwards, right? What the neural network will do is it will find where the objects are, estimate a probability of whether there is an object there in this particular space, and where the edge of the objects might be. And therefore it knows that's an object, and that's all it looks for. What we tell it is there's an object there, there's an object there, there's an object there. It doesn't really care. The neural network doesn't really care the absolute value. That's something that's assigned afterwards. Okay. Now you say across images. If you're talking about tracking nucleus over time, then that's something you do in post-processing once everything's kind of segmented, right?
No. I was indicating that if you have a number one label in one image, mm-hmm. then it isn't necessarily the same as the number one label in another image.
No,
but you explained that the labels itself don't really matter.
And they are in fact they disappear. The network doesn't see those numbers. It just sees objects and where they are and their shape, and tries to match the number, the places, and the shape of those objects.
So underneath it kind of gets the same pixel-based classification, or is it also counting the number of objects that it expects in the?
He also gets a penalty whenever he fails to identify an object, and he also gets a penalty and learns from it if he identifies an object but identifies its shape wrongly. And that's how those penalty help the neural network to tune its own parameters to slowly improve to get towards the target image. Okay, so it gets penalized by every time it gets anything wrong, and that's the iterative process effectively, right?
Yeah, I was kind of wondering how that kind of a learning function would work, because with pixels it's clear it's right or wrong, and here you have multiple different features that you can work with.
You're perfectly right, and that's what computer scientists are spending their days doing. Okay, trying to work out what's the best way from an error to translate that error into a quantitative value that can then be fed back into the neural network. And unfortunately, we don't really have time to explain how the mathematical functions of the so-called loss functions work in this case. But we could take that offline afterwards if you wanted. That's absolutely no problem.
I was just curious because it's so usual that it's just pixel based. So I was wondering what kind of features were used here, but you explained it quite well. Thanks.
Yeah, that's right. And in this particular case of Stardust, it'll be estimating the probability of an object being there and the possession of the different radio exploration that it's looked at, right? That's why it's looking at star-shaped objects. Yeah. So in fact, so thanks for your comment, by the way. That's great. In fact, we will not be starting playing with, we will not start playing with Stardust, but we'll start playing with noise to void, just for in the interest of how we've structured this, this workshop. And noise to void, unlike what I've shown you so far and what you've seen very often, does not actually require the ground truth output data set. Okay, the ground truth target data set. And so Stardust, you provide it an input and a target, and it tries to match per image the target. That's a so-called supervised learning method. In the case of noise to void, and that's why we wanted to show this to you, it uses a learning method which is called self-supervised, or sometimes you hear the term unsupervised mode, because it can learn directly the training from the data itself. Sorry, it can learn the target directly from the data itself. So it doesn't need the equivalent denoised image, okay? Just to say a very few words of how this is made possible in the case of noise to void. The authors of this work, Florian Jung and others, have actually devised a very smart method, I think, to do this by taking the initial, taking a training data set, such as a noisy image like this, cut out some pixels that will become blind to the network, and train the network to predict just a few pixels from this image. Then cut out a few other pixels and try to force it to predict those pixels. And over time, the only redundancy that happens by predicting those pixels are the denoised underlying structure and not the noise. The noise is completely random, it's unpredictable in nature. And therefore, by forcing it to learn a predictable underlying structure, that's inherently producing an image that will be denoised. And I think it's an absolutely smart idea that makes things extremely powerful in this case, because it's very versatile due to the fact that you don't actually need to even provide the ground truth data set that accompanies the training data set. So in the particular case of one use case of noise to void is the one we're going to be doing today, is to provide, is to want to denoise, say, a time series of, say, a fluorescence, a cell migration assay from fluorescence data like this. And as we said already earlier, using low power is great for time courses because we reduce phototoxicity. But only from, say, one of the frames, of our very same time course series denoise the rest of the time series. Okay, so that's what we'll be doing. In practice, we could use more frames as training data set and then apply it to the rest of it. But just for today, just to show you the strength of this approach, we'll be training only just one frame and then applying it to the whole stack and recover a denoised stack afterwards. Okay, so if this makes sense, I think, so that's the data set we'll be looking at. If this makes sense, I think we can just crack on and look at ZeroCost GitHub. So let me just paste this again for you. If you guys travel to this page, that's our GitHub page where we host all of the information for the platform. And that includes tons of useful information adjacent to training, to how to understand deep learning and so on and so forth. But importantly, so that's a great place to fetch some information and to be on the lookout for useful tips as well. But on the wiki page that you can join by joining the wiki tab up there, we also importantly have a list of all the notebooks that we have currently integrated within the platform. And so just to take you through this table very quickly, here are the name on the left, the name of all the different networks that we've implemented, the relevant papers. As we said, what we provide is a platform and not new neural networks. We integrate neural networks as they get published, and the different tasks that they may be useful for. So from segmentation, denoising, or so funky business like image-to-image translation, the things that you've seen from Guillaume on predicting nuclei from actin dataset, for instance. A couple of data set that you can download and play with. The stuff that we'll be looking at today are from those type of data set. And importantly, on the right, a way to access the actual notebooks, okay, and to start actually doing the work. So we'll be doing taking a look at Noise2Void 2D today. So I will be just right-clicking or shift-clicking onto this Colab button, and that will open a Colab page. And there we are. We're now entering the world of Google Colab. As Guillaume highlighted to you this morning, Colab will then provide us with basically a little machine. What I mean by machine is a computer, essentially, that sits in the cloud, that will be to which will be associated a little bit of memory, some computational power, and importantly, a high-end GPU to be able to do all of this. So all of that computational power is shifted into the cloud. So what we have here is basically just a web interface to be able to communicate with that computer and tell it what to do and how to handle the data that we will be providing. On the left right here, you see a table of contents that recapitulates the complete workflow of deep learning, from initialization of the session, installing the different bits of software that just take a couple of seconds, setting some parameters, and I think that's where we'll spend a bit more time thinking about that section, the section of training, and as highlighted over and over again, the section of evaluation of the performance of the model. When does it work? When does it fail? And so on and so forth. And a last section right here, section 6, which is about using a trained model that you will have validated along the way. Okay, so if you guys are all with me, we can get started on running some of those things.
So, Romain, maybe I can stop you just for 1 second. So
yes,
one thing that I think here is great to highlight is that all the zero-cost notebooks are exactly the same. So they all look the same, which means that when you learn on how to use one, then you will open the next one, and there's no reason that you should not be able to use it straight away. So it's exactly the same.
Yeah, I'll just open the Stardist to prove your point right here. If we open the Stardist that we'll be using a little bit later on, you see immediately that the table of contents is strictly identical and the structure is identical. And that also makes it a platform that becomes highly usable and versatile, as Guillaume was just saying. Okay, thanks. as always, right? And that's the last time I will be saying it. You can interrupt me if there's anything that's not working on your end or there's anything that's unclear to you. Okay, so let's just start straight away. So we've included a lot of text to help you to guide you essentially through how to use it and how to set all of the different parameters. But let's do it together. The first thing to do is to initialize the actual session. So we'll be essentially setting up that little computer in the cloud for us. And but simply by clicking on the arrow on the left right here, we'll be running the underlying code that's sitting underneath. And I will be showing you this in a second. So now it's doing this. It's executing the underlying code and is giving us some outputs, right? A couple of things. First of all, we now know that we have access to a specific machine with a specific GPU. The type of GPU we have now is called a Tesla K80. Tough luck for me, this is the worst that's available in Google Colab. So you guys might have different ones and some that are more performant, and so your training will go faster than mine. The other thing that's useful to notice is on the top right corner right here, you see that you've got RAM and disk available, and it tells you that we've got about 1 gig of RAM out of 12 that is currently used, and 32 gig of disk space out of 68 gigabytes used. And all of this refers to what's in this computer that's available to us in the cloud at the moment. Okay, so we now have a bit of RAM, a bit of disk space, a GPU to play with, and we can just get started. If I double click onto this, you can actually start seeing the code underneath, right? Nothing's hidden from you. If you guys wanted to, if you are a little bit Python educated, then you can go and take a quick look at what's actually executed underneath. But we don't really need to know or see this for executing anything at all. So now we have a machine associated to us. The next step is to actually tell that virtual machine where to go fetch the data that we're going to be playing with today. And so that's done by mounting, so-called mounting the Google Drive to the session. And so by running this gives us a link that we can therefore access. And by allowing and going to get an authorization code, we can now paste back an authorization code that will essentially give access to the session. We'll give the session access to the data. Okay, so this will take just a few seconds. Let me close this. Mounted. Okay, so the important thing is now on the left, we can go onto G Drive. We've got a bunch of folders available. And now if you look into my drive, I've got all the data that I currently have in my own Google Drive space. Okay, and so if you're also at that step, you should also see all of your different folders available right here. And this is how we give access, notebook access to that data. And just to show you, I've also got the two different folders that I've copied over right here that we'll be playing with today. Yeah. Any questions? All good? Excellent. I'll assume it's all running smoothly if I don't hear anything from you guys.
It's running very smoothly, at least. Yes.
Excellent. So next step, now we've got mounted, we've got access to the data. Let's just install everything. Again, all the installation code is underneath. We don't need to see it. This bit of code will actually simply execute itself and go fetch the data, arrange the different libraries in the way that is necessary to execute this specific notebook. And that's one clear advantage with running things a little bit of a sandbox in the cloud is installing all of those libraries will need to be installed in different ways for different networks. So if you were running several networks on the same machine, you will probably have to reset the machine quite extensively for each network that you need to use. And that makes it very difficult to actually use local machines because of this. unless they're all part of the same ecosystem, for instance. And but that's rare in the case of performing lots of different tasks. So now the notebook is kind of set up. This execution's over. We can now start thinking about setting the different parameters.
Romain, can I
Yes,
stop you? Sorry.
Absolutely.
At the end of the talk, there was a couple of questions about privacy and then running the notebook locally. So could you show the requirement text? I don't know if the person who asked is actually in our room, but maybe you could show where the requirement text is.
Yeah. So if I go back onto the drive, locally onto the memory of the local machine that's in the cloud, the notebook has automatically created a requirement.txt file, which if you run stuff locally, you'll know you would need, and that will list up all of the different packages and the version of the different packages that are necessary to run this notebook. So this requirements.txt file is what you'll need to run things locally and basically avoid running things in the cloud, right? And that's automatically generated right here in the local memory. Yeah, does that answer your question? That was what you wanted me to show Guillaume, right?
Yes, thank you. And it's generated for all notebooks. So if there's a notebook you want to run locally, then you can find it there as well. And there's information about that on our wiki page.
Excellent, thanks. So,
sorry, can you please show us again how to open this specific notebook, because I can't find it.
Okay, so I've copied in the chat the link to the GitHub page.
Yes, I've got the link, and I'm there.
You're on the wiki page. There's a tab for wiki. Yeah.
Yes.
You're on here. If you we've opened Noise to Void, which is right here. Yeah. If you use the Colab, open in Colab tab, you can right click, open in a new tab, and then that'll open. I'll be opening just a separate one again now, and that'll open the notebook that you're seeing right now. The only difference with the one you'll have is that mine's got a black background because I prefer. I find this a little bit easier to read, but that's the only difference between yours and mine. Should be.
Okay, so I need to go to the Noise to Void to the Colab, open in Colab.
Here,
and
you see my mouse?
Yes, I opened it. I think I can't see your mouse.
Yeah. So if
yes, that's what I did. Okay.
Awesome.
Thanks.
You're good? Excellent. So you've got a little bit of catch up to do, but as you've seen, there's running those things only take a few seconds. So now we're getting into the important part of that workshop, is to think about how to actually set the different parameters for a successful and efficient training session. In our section 3 of each notebook, it will be about setting all of those parameters. The first thing that we have here is a set of text and parameter description that will guide you through what each of those parameters mean and how to set them up, essentially. There is some variability between networks because some parameters are, although some parameters are the same across the different networks, some networks have specific parameters that need to be set, in which case they are accurately described in that part. But let's take a quick look directly at where to set them up. And we set them up in here. The first parameter in this particular notebook that we need to set is where is the training source data. So we need to provide it a path to where the data is. And luckily, well, not luckily, but intentionally, we've got our Noise to Void folder right here. So okay, I've got 2 additional folders that you guys don't have, which is from me having run these beforehand. I've got one folder that's called models and one folder that's called predictions. You can ignore those for now. But importantly is in training, in this folder, we have placed all the training data set, all the training images, and I can right click, copy the path, and then go and paste it back into the training source. So now this is set, then the network or the session will now know where to go fetch the data for the training. You'll know that everything that's in this folder needs to be used for the training stage. Now we're going to need to set the model name and the path to the model. That's what I had created earlier, but I will be recreating it for you again. You can right click and create a new folder. I've decided to create it into the same folder to keep things easy, and I'll call this model 2020-12-02. That's the date of today. Everything will be creating today will be in there. So you see the folder being created right here. You can also right click and then put that into path. And so now that means that the models that we'll be creating, right? So the trained models will be saved in there, and they'll be directly saved because I've given it a path directly onto your Google Drive. Therefore, they will be saved directly onto your Google Drive. And so that's also something important to remember is you can just let the session run and expire. Everything will be saved automatically. The other thing is we need to give it a model name. I'll also give it today's date, 02, noise to void model 1. Okay, and so that's the model name. Okay, we've set up model path, number of epochs. So as you've heard about how training happens and how it's an iterative process that the network goes through the training data over and over and over again, fine-tuning its own parameters to get slowly better at the task that's at stake today. We need to do this iteratively. And the number of iterations is one of the parameters. In the world of deep learning, those iterations are called epochs. And so a typical number of iterations that's useful is, for instance, doing 100 iterations, okay, for this particular network again. In each notebook that we have, we've given sensible default values so that you can get started relatively easily. And we'll see in what cases it might be useful to decrease or increase those number of epochs as we go along. Patch sizes. Although the data that we've looked at here for training is 512 by 512, right? We've looked at it. What will be fed to the GPU for training will be only small randomly selected patches of 64 by 64 pixels, randomly selected and extracted out of the image, and you can decide the size of it. Okay, that has an influence in terms of how it trains, of course, but that has also a major influence in how the memory is handled onto the GPU. In this particular notebook, small patch sizes of 64 are great because then, as I was saying earlier, you've got a 64 by 64 patch. It'll remove a handful of pixels, a certain fraction of pixels, and then try to predict those pixels, and then do this over and over again without having an enormous context of a large patch. Okay. Batch size and number of steps. Those are already advanced parameters in here that for initial uses of those notebooks, you don't necessarily need to worry about. But for each epoch, the batch size basically determines the number of patches that are fed into the GPU for each step of each epoch, right? So one epoch is one big batch, one big iteration. Within one epoch is going to do a number of steps, 100 steps per epoch in this case. And for each step, it will be feeding 128 patches that will be generated from the training data, okay? So in this particular notebook, we need a very high batch size. And that's, we've established that for stability of the network, that's really important. this is a little bit of a trial and error kind of approach. There is a certain level, like for every tool you'll be using, there's a certain level of learning what works and what doesn't work. Okay. But those sensible, importantly, those values are sensible to start with, and they'll work in the majority of the cases to get started. And only fine-tune optimization will require you to kind of start playing with those. Okay. So now we've got all of those parameters set. All I need is to run this part of the code. And it'll be initiating the parameters, and it'll also be showing us the data set that was selected for parameters, for training, sorry. And so that's the image that we had a look earlier. Next step, and you.
Question?
Yes, sorry.
Can
Hello?
I ask a question?
Of course you can.
For the batch size, is there a specific strategy for that? Does it happen to coincide with, for example, the size of objects that you want to recognize, or is it just also kind of guesswork what that would be?
So in this particular case, and actually very often, your network will work best if it gets many examples. So the more examples you give it, the better. So in fact, the batch size is a way to fill up the GPU memory, so it at every iteration of the GPU execution, it uses as many examples available as possible. So in this case, it's not, the batch size isn't related to the number of objects, but
Oh, sorry,
it will
batch size.
Oh, patch size. Sorry, I misheard you. Yes.
It might be that I said the wrong thing.
No. I misheard you. Sorry, my bad. The patch size, it typically works for small patch sizes in this case. Of course, what really matters here is the patch sizes shouldn't be too small so that it's only noise, only background, say, for instance. But apart from that, something that is kind of big enough but not too big is great. Right, I know that doesn't really mean anything, but in this particular case, something like 64 works well. But if you have a good idea about what's in your image, you can actually match this so that you're making sure that 64 by 64 will catch some signal and some noise in all cases, if that makes sense.
And should it always be a square number?
Yes, it needs to be square images because that's what the network will expect. So that's why we provide only one parameter in this case, because it'll be both width and height.
Oh, okay. So this is not 46 pixels. This is 46 by 46.
Yeah, that's right. Yes.
Ah, okay.
Yes, exactly.
Yes. Thanks.
No worries. So now we've got all of those patches set up. We can move to the section of data augmentation. You've heard from Guillaume how useful that can be. In this particular case, the implementation of data augmentation we've got in this is some data augmentation that will perform rotation. So imagine 90 degrees or 180 degrees on the data. So that will already kind of make things a little bit more diverse. And also flipping those images. So left, right, top, bottom, and left, right. Okay. And so again, data augmentation will really help with learning, getting the network to not rely on specific orientation of the data to do this denoising, and rather be more general to the structural content rather than the specific orientation of the structural content, if that makes sense. So we'll be running some data augmentation. I've got this ticked. Let's run this. Okay, data augmentation enabled. You've also heard again about another tool that we've implemented in here is the capability of using pre-trained model to initialize a training. For today, we'll start from scratch. So we'll start by a model that's completely randomly initialized. All the weights are randomly initialized, and we will not be using a pre-trained model. So I will just be running this with this unticked. We might get back to this.
May I ask a question?
Yes, of course.
So I've got two questions. One is increasing the number of epochs not necessarily means you will get better results, right?
Correct.
So that's one question. And the other one about the data augmentation. So we can see what are the possible augmentations that that it use, like because there are many kinds of augmentation. So
Yeah. So
and is it possible to add like a new type of augmentation?
Okay, cool. So let me get back to your questions. First of all, the number of epochs. You're perfectly right. There will be a number of epochs after which, an epoch number after which, nothing useful will be learned anymore. And in which case, well, training should either be interrupted or the network at which it stops doing useful training should be remembered in one way. So we use the latter approach at the moment, and for all of our notebooks, the network will be able to pick the best epoch at which it performed performed optimally before the training started becoming detrimental in a way. Okay, so there is a way to, even if you let it train longer than it needs, first of all, you'll just be maybe wasting a bit of computational time, which isn't necessarily a huge issue. But second of all, and importantly, the network is able to remember at which point it was better, right? So even it's not necessarily going to take the very last iteration. They might take a previous iteration because it figured out that this previous iteration was better than the last one. So that's an important component. Now, back to data augmentation. Each notebook will have different kind of augmentation, and that's explicitly stated what kind of augmentation is implemented for each notebook. In this particular one is rotation and flips. And of course, it would be straightforward to import code from other notebooks into those sections to implement different types of augmentation. But we've tried to match what was sensible and what we've seen was useful for each notebook, and also what was suggested by the original authors as well of those individual networks. And so just to give you another example, if we go to Stardist, here in the case of Stardist, we've got a lot more possibilities, and that's all performed by a Python library called Augmentor, for which we also have a separate notebook. So you can also run, you can select your patches and run your augmentation separately if you wanted. But for this one, it's got zoom, magnification, distortion, shear, image shear, magnitude, and so on and so forth. Okay, so you could do, there's a lot more that can be done at the augmentation stage apart from what we've implemented in Noise to Avoid, absolutely. So does this answer your question?
Yes, thank you very much.
Yeah, excellent. Cool. So getting back to training. So training, section 4, we've now set up all the different parameters. We've told it to do data augmentation, to load a pre-train, to not load a pre-trained network, but initialize everything randomly. Section 4 is about actually initializing all the different variables that it needs and set everything in place. Look at the patches and create the patches. That's what that first 4.1 section is about. And so we can take a look at individual patches. And if I go back up at the original image, the patch that we've got right here is actually a small subsection of this image here. And because a lot of noise is present in here, unluckily for this run of it, we're showing a random patch out of the hundreds and hundreds of patches it's created, a random patch that will have only been located into the noise. But that isn't a big issue. So now what's left to do is to actually tell it to start training. And that's as easy as just getting it to run this part of the code. So let's take a quick look at what's going on for the first few iterations. So it's going to start initializing a few things. And there we go. Epoch number 1, epoch number 2, and it keeps going. And in this particular case, for my settings and my notebook, sorry, my GPU allocation, you can see that it's about a second or so per epoch in this case. If we had used more training data sets, if we had used more epochs or a higher batch size or a higher number of steps, we would therefore be, each iteration would therefore take longer, and the whole training would take a bit longer. In the interest of time, we've set things up so that it can execute fairly rapidly. But you'll see that it's already going to be doing, hopefully, a fairly good job. Everything's managing to run. Everyone's managing to run things. Everyone's tagging along nicely.
Sorry, short question. Maybe I missed it. What exactly is the learning rate, and when does it decide to or decrease it? Okay.
Yes. Very good point. So you remember from Guillaume's talk, the learning rate was part of that backpropagation algorithm, and the learning rate actually tunes how big of a change in weights we perform at each step, depending on the error. Okay, the larger the error, the larger the step. But we also have a little tuning factor to set how those steps, how big those steps are. So there's two things. The error will define how big the steps are, but that learning rate will also depend on that. Now let's go back to up there while this runs. That doesn't influence the training.
Romain?
Where was it? Yes?
Here we can see the quality of the training after it has finished. Is there a way to monitor during the training, like the loss of function or stuff like that?
Yes, actually you can see, if you see on the right, for each iteration, it's not plotted, but it's indicated. You can see the values here, the MSE and the absolute value, and the validation loss and MSE at the validation are the values that it's trying to optimize, okay? And hopefully you see things kind of oscillating, but slowly going down. Does that make sense? Those values right here. Yeah?
And Christophe, so if it's something that's very important for you to see the curve as is being generated, and it's something that we can add as well.
For something that takes like 2 minutes, like here, it's not a problem. But if you start to train for hours, it can be useful to see that something goes wrong and stop it before you wait for the end of the training.
Mm-hmm. Yeah, no, that's a good point. Yeah, that would be that we can put this on the list of things to implement for our next release. That's absolutely useful. Yeah. Just to finish off on the learning rates before I forget, the learning rate is set right here, of course. It will be, that's a sensible value to start with, right? We always provide default values that are sensible. You will, if you see that your training doesn't converge quickly enough, you can increase this a little bit. If you see that it converges towards something that doesn't work very well and you're willing to wait a little bit longer, a few more iterations, then you might want to decrease the learning rates and increase the number of epochs, okay? But there's something that's also internally set that I've not told you about, is that's the initial learning rates that is set in here. And internally, the learning rate is actually slowly decreased as the performance of the network increases. So it takes finer and finer steps automatically during training, and that's done under the hood without without you having to control this. And so in most cases, and the majority of the cases, the way this is handled by the network actually works really well. It decreases automatically in a way that allows for finer and finer tuning efficiently. Sorry, does that answer to your question as well?
Yes, thanks.
Yeah, excellent. So Christophe, yeah, I was showing you values are here. We can plot them. And let me show you immediately then the curve, since we're talking about it. So the training is finished, right? It's told us that it's completely executed, is successfully executed the training. We can now switch to evaluation. And one of the evaluation is to actually visualize those values, those loss values that we were talking about. And that is done in the first part of that quality control section. We can first of all run this. That allows us to tell the session that we will be doing the quality control on the model that we've just trained, as opposed to loading a previous model that we've trained yesterday and on which we want to learn, on which we want to evaluate some the performance. And we can now run this 5.1, which is inspection of the loss function. And that will give us a display of how the training and validation loss have evolved over time, right? So your curves will look most certainly different from mine, because remember, we're all running different sessions to which the initialization, the random initialization of the networks are different because they're random, and therefore it will start from different starting points. Okay, but the important thing is that it decreased really quickly, then plateaued, and kept decreasing more slowly, but still steadily towards until the end of our training session, and everything runs smoothly. And you've seen curves from Guillaume earlier as well, curves in which validation loss might kind of shoot up after a certain point. That's when overfitting happens. And when this happens, that's when the notebook is capable of going back to the point, to the epoch, to the iteration, specific iteration at which right before it started overfitting, and actually use this for prediction afterwards.
Is it normal that the validation loss ends up less noisy and a bit below the training loss?
So I've also noticed this, and I actually don't have an answer why this is less noisy. My only intuition on this is that the validation loss will be performed on fewer images than the training loss, and therefore there's, to a large extent, lower diversity in the validation loss than the training loss, right? But that's not something that I've investigated enough to be able, it's what's going on for sure. Would that make sense to you?
I guess you have more kind of outliers in the training, so it's more noisy, and the average is a bit above. So.
Yeah, exactly. Yeah. Excellent.
Romain, can I stop you for a second?
Absolutely, you can.
Before you go too far in the notebook, it might be worth showing the model folder.
Yes.
And then mentions the report and so on.
Yeah, it says that you should download it, but you should download the whole folder, because there's no option to do that from the drive here.
Okay, let me take you through it. Those are absolutely
section 4.3.
Yeah. So let's go through this. So remember, I've created a folder, a model folder, and inside this itself a folder for that specific model that I've just trained. So if we're going to train more models, they'll appear at different folders as different folders right here. But in this specific folder, we now have all the data that was generated through that training session, the quality control. So that's the stuff that we've just taken a look at. The weights right here. And as I was telling you just earlier, the best weight might not be the same as the last weight. So those are saved as separate files. The best weight is the one that is saved right before it started overfitting, if it did. There's some test outputs images. There's a model export that will be compatible with running those models on other platforms, and we'll talk a little bit about this. There's a few more kind of bits of information that's useful for the model, but importantly, there is a PDF PDF export here, okay? And let me show you two things. One, the easiest way to download the entire model would be to go back to your Google Drive folders, go right here and actually download it this way, right? That's purely an annoyance of Colab that doesn't allow us to download entire folders, but only individual files. So that would be the easiest way to download the entire model, okay? But it's saved on your Google Drive, so you might not need to download it unless you're scared that your Google Drive might disappear at some point. It's important to download it if you're going to be running things locally afterwards.
Sorry,
Okay.
Romain, can I stop you? Can I stop you again for a second?
Yes,
I'm actually curious to ask for feedback on this from prospective users that you guys are here. How do you feel like everything is now saved and safe on your Google Drive, and that's how we've always used it? But will you find it useful to have a button here where the whole folder that contains the model will be zipped and downloaded to your computer? Because that's something we could very easily add here. But is that something that you will find useful, or having it in the Google Drive and finding it there later is fine?
I think it would be useful because the section 4.3 says download it, but it doesn't explain that you should go somewhere else to download it. So either remove that section or put a button here to do it. Or explain that you should go back to your Google Drive to do it, because I read that and so I right click on the sidebar thinking there would be a download option, and there wasn't.
Fair enough. Thanks, Christophe.
That is a very good, useful feedback, actually. We don't want you to get stuck at any point in this workflow, for sure.
The problem is that when you don't know exactly what you're doing, you just are very careful to do exactly what is told you to do. So if you just go at that point and you're like, maybe if it fails, it will be because of that. So
no, absolutely. Just to make extra clear as well, if any of what we do is unclear, you want to get back to it, we've also got a video right here onto the wiki that will re-explain all of this in detail, including that part of the workflow as well. And so that can be also useful to go through some of that extra material whenever there's anything that you need to troubleshoot along the way.
And maybe useful to remind you that everything is recorded, this session here for I2K, and will be available. So everyone can go back to the workshop and listen to it again.
Absolutely. So importantly, we can directly download that that little PDF that was saved into that folder. So let me just do this. You can right click, download. There you go. And let's open that PDF. And let me close this. That PDF is saved for every single training session that you would run. And that's essentially a report on what you've just done, reminding you how every single parameter was set, which version of each package was used, what GPU, everything, basically everything you need to know to basically recapitulate that training. And so in particular, this can almost be copy-pasted directly into your material and method section of your paper whenever you use those different tools. It tells you where you got your data, how it looked like, a couple of references, and so on. So that's also quite a useful thing to get back to whenever you're going to be running some network optimization and starting tweaking all of those parameters as we have just discussed. So going back to this, now that we have done some training, we have a model, what we can start already playing with is to go straight away to try using it. And let's take a quick look at how it will look like if we try to...
Can I ask one more question?
Of course, yes, please.
So for the output under 5.1, I see that your training and validation loss curves meet in the end and really overlap. And on my screen, the orange one, the validation loss is still higher than the training. So is there anything I can do at this point to evaluate whether I'm doing okay or not?
Okay, yeah, really important point. Yeah, thanks. It will every single curve will look different, but importantly, maybe that's something we should also add in here. That's a good feedback. The absolute values are almost irrelevant, and what really matters is the evolution of the absolute of the values. Okay, so if it's shifted up or down with respect to the training loss, it really doesn't matter. It depends only on which patches it's selected for validation and for training, which will be different for each one of our sessions, of course. What really matters is how it evolved over time and not the absolute value. So if it's shifted, you can just ignore it.
Yeah, because I already noticed that my training and validation was vastly different, much more different than yours. So that's probably then why they don't meet in the end.
Yeah, exactly. But
Okay.
do they both look like they kind of going down, plateauing, and then
yeah, they both
slowly
plateau, just at different levels. Yeah.
Then that's all you need to know at that stage.
Okay, yeah, that's clear. Thanks.
That confirms to you that you've not overfitted and that it's converged towards a place that is it's actually confident with. And the fact that it plateaus right here is actually, the moment it starts plateauing right here is when actually the learning rate gets adjusted automatically. So it starts suddenly decreasing the learning rate and doing smaller and smaller steps. And that's why it only slowly converges towards something more sensible. Okay?
Yeah.
So we'll be doing 5.2 in Stardust in the interest of how we've structured our workshop today. So I will not show you 5.2 on Noise to Void, but we'll take a look onto Stardust so that we can already take a quick look at how to use this trained model. So we've not fully evaluated it, but we can already start playing with the data and seeing whether it does a sensible job at the full time course that we've got. Okay, so let's run section 6 together. Predictions from unseen data set. For this case, we're going to be similarly selecting now the test images, which is what's got all of the rest of our time course data set shown right here. So we'll be right-clicking, copying this path. This is the data we now want to process from this trained model. So the model is still in memory, and we can tell it, okay, where are you going to save the processed and denosed images? That's the result folder. And similarly, in the past, I had created a prediction folder, but I'll be creating a new folder for us today. A new folder right here. So predictions 2020-12-02. That's our predictions. There you go. Right click on this copy path result folder. So we now the session knows where to get the data to process, and it knows where to save the processed data. Okay, and that's again directly onto our Google Drive. So that means that we can access this directly into the Google Drive once this is complete. And similarly to before, we can tell it, okay, use the current trained model, the one that's in memory, the one we've just trained, or we can use a previously trained model by just giving it the folder of the trained model in the past. So we can go back to this and then go straight to section 6, just run section 1 for installation and go straight from section 1 to 6 and actually run the prediction. Sorry, let me just check one thing. Yeah, sorry, you need to run 1 and 2. You also need to run the installation part. So 1 and 2, and jump from 1 directly to 6 if you're gonna be running predictions and not retrain.
What do you call the path to the model? Is the path to the folder?
It's the path to the folder.
Or the path to a particular file inside the folder?
No, it's the path to the folder because it will need to also fetch some other files into the same folder. Okay. So the way I would do it in this case is take this folder right here. That's the copy path. I could put it in there, but that's irrelevant in this case. And I would paste this path. Okay. So there you go. We can run this, and it's gonna go through each one of those images one by one fairly quickly in this particular notebook. you see how it goes through each data set one at a time. Let's take a look at what's going on in prediction. In prediction folder gets populated as well. And now it tells us that everything's been saved and processed and it's basically done. Okay. And 6.2 in this particular notebook will allow us to just take a quick look at what's happened. Okay. So, and what this will do, it will fetch one image, will fetch the equivalent denoised image, can take a better look like this, input and predicted output. And you can see already that it's a lot less grainy, and we've improved the signal to noise ratio quite well in this case. But then the next step, is everyone good with this? Yeah? The next step I would say right now is to go back to our notebook, sorry, to our Google Drive and our different folders. And we've got our folders that have appeared here because we've saved directly on it. And what we could do is download the whole folder from the predictions. So Google Drive will zip this and will send that right back to my download folder. That will take a minute or so. There you go. Okay, so now we can go back to Fiji and take a quick look at what we have obtained. Let me first load the raw data so we can take a quick look. Raw data here. Load. There you go. Image. We can just transform all of this as a stack. So we'll call this row stack. Okay, and we also have in here in download, for me, it'll appear in download, the predictions, right? So I'll just be copying this right onto the desktop, opening this. There you go. Similarly, let's copy this into Fiji. Okay, let's build a stack out of this, so we can compare directly. In this case, it'll be useful to call this prediction. Okay, and now you can see that we can put those two guys side by side and maybe even sync those windows. So I'm going relatively quick here because that isn't a Fiji workshop, but if there's anything that you need help with, just give me a shout. And now we can therefore zoom onto the different parts of the images and also go along. There you go. Let me just improve a little bit the contrast, the display contrast on those guys. Yeah. And you can now already directly assess the improvement, the signal to noise improvement in that data set. Okay, and so the grainy structure that's present in the noise in the background here is gone because we've improved the signal to noise. But you might also see that there is a little bit of structure that has appeared in here. Okay. So that would tell me that maybe adding a bit more training data sets and maybe training for a little longer might improve also those kind of mini patterns. Okay, so you can also start picking up things by purely a visual inspection is already quite useful. Okay, so guys, if there aren't any questions, I will give you a minute or so to think whether you have any questions. I see that there's been a bit of activity in the chat, so maybe Guillaume's been tackling all of those, and that's great. That gives me a bit of flexibility. This basically ends the workshop, the part of the workshop on noise to void. And actually, I will hand over to Guillaume for the stardust part. Is that okay for you, Guillaume?
Yeah, that's perfectly fine. Yeah.
Yeah.
I was going to type the answers into the chat, but maybe I can
do that.
Take over that.
Okay.
So yeah, so I think now maybe what we can do is take another 2-minute breaks if you're all good with a noise to void notebook. And then if you still have questions about it, then please shoot. I'm happy to answer as well, or type them in the chat, and Romain will answer those. And then we can start with the StarDist part of the workshop in maybe 3-4 minutes. If that sounds okay.
And I'll be troubleshooting. Well, I'll be answering your questions in the chat as well, like Guillaume was doing during the previous workshop.
I have a question, Romain.
Mm-hmm.
So if I understand correctly, the way it works is that it removes some pixels and tries to determine what are their value based on the neighboring pixels. And if it fails, it means that it's noise. If it manages to do it, then it's not noise. But if the details, if you call details things that are just 1 pixel in size, it's basically make them disappear too, right? So there's an amount of smoothing that goes into that. So you will smooth your image by applying that anyway.
Absolutely, and you can, if I go back to okay, I had just closed them. If I just open just one of them, you can actually see that yes, it has smoothed it a little bit. So of course there is an element
because
of smoothing.
if for example, if you do an unsharp masking with a 1 pixel size on a typical noisy image, you will retrieve some details that is not noise, and that is the kind of detail that disappears here.
Mm-hmm. Yeah, no, that's true. Absolutely true. Yeah, no, that's a very good point. So nothing's perfect. If that's a concern, of course, care and other denoising approaches that are taking a different approach, a more classical and supervised denoising approach would also work really well and would probably kind of start filling those gaps in very different ways, right? But that's the downside.
I think in the manuscript, it's stated that noise to void is not good to remove to remove artifacts from scene images, or
Yes.
and I guess that's because it's not a random pixel to pixel noise, right?
Yeah, exactly.
It's a structuration of the background based on the structures that are there. So
yeah, noise to void in the case of slight patterns that's in the back, it'll think it's structure. It'll denoise those structures.
yeah.
So yeah, of course. Whereas in the case of care, sorry, you want to head off? You want to get started?
No. I don't want to get started. I just wanted to add that they actually have a different version of noise to voids that specialize in removing structured noise that they're working on for sim denoising, for instance. So it's exactly as you said, Christophe. So noise to void, and especially the ones that we have here, is very good at denoising, let's say, noisy confocal images or EMCCD camera where you have a really random pixel noise. But as soon as the noise is structured, then it will completely fail and identify the structured as being signal. And then for that, care is much better, or variation of noise to voids, which is specialized for recognizing this kind of structural artifacts.
Okay.
Okay, so is everyone back? Is everyone okay with that? We get started with StarDist? Of course, as always, anyone who is not back will not be able to tell me they're not back. So maybe we can wait 1 more minute. But if you're here, then one thing you can already do is go back to our wiki page, where you can choose the different collab notebooks that are available. And then the ones that we're going to use now is StarDist 2D. Is everyone okay with us starting? Okay, let's start. So as for noise to void, if you want to open StarDist 2D, then you can right-click in the Open in Collab button and then open it into a new tab. And then what you're going to have is basically a notebook that looks very similar to what you've just seen, but now is to train StarDist and on noise to void. But other than that, the interface is exactly the same. You have a mix between cells that contain text to explain on what's going on. So some useful references for the StarDist deep learning network and the structure here of the whole workflow. As for noise to void, you can connect to a session here, and you can have access to your files there on the side. So one thing that I'm not sure if Romain remember to show you that I will show you here is that, of course, you have a lot of different options here, but one that's really useful for you to do is to click on File and then save a copy of the notebook in your own Google Drive. So what do I mean by this is that at the moment, the notebook you have here, you can open it straight from our GitHub account, and that's perfectly fine. But the main issue is that nothing that you do to the notebook is saved. So if you want to go back to it later on, you will start again from a blank and fresh notebook, which is fine if that's what you want to do. But here now, if you've created a copy that is saved in your own Google Drive, then now everything that you do to the notebook is saved and you can have access to it. So it looks like maybe I've crashed. Oh, no, as always, because of Zoom, I can't access the tab. Okay, now we're sorted. So now you will have a copy of the StarDist notebook, which is yours. So if you want to do modification to it, if you want to change the code, then everything will be saved in your Google Drive. And the other advantages of making the copy is that the connection between the notebook and your own Google Drive is also faster because they live on the same space. Okay, so here is a notebook. To initialize it, it works exactly like for noise to void. You can run the cell here to see what kind of GPU you will get allocated now by Google. So it's always a little bit of a lottery. And so one of the things that you can consider is that if you have a training session that you know will last a very long time, and then you don't get the GPUs that you want, then you can always restart the session a few times until you get the ones that you want. So here, for instance, I got a Tesla T4, which is quite a nice improvement compared to the K80 that Romain got for his session. So that's one of the perks of living in Finland is that because we are a lot less populated and there's not many people using Google Colab, and because part of the allocation is geographic, we get some often nicer GPU here. So I can't see any of you and I can't see the chat. So can someone just tell me that you are still all here and that you can hear what I'm saying?
Yeah, we can hear you, or I can.
Wonderful. So yeah, so you can initialize the session. First thing to do next is, of course, to mount your Google Drive. So you can do it here. You have to click on the link to give the authorization to the Google Drive and allow it. And then you can copy and paste the code here. So I'm going to close that one because Zoom is stopping me from accessing my tab. And then it will take a couple of seconds for loading your Google Drive. And now your Google Drive is mounted, and then you can access it here from the side. So the same as for the noise to void notebook. And then the first thing you do, of course, is now install StarDist. So that's one of really the strength of the Google Colab platform is that every time you start with a fresh environment, which means that you don't have to worry about the dependencies too much because we work very hard to ensure that the notebook works. So if you have to install everything locally, then you will have to fight with installing those dependencies. And for instance, the dependency between StarDist and noise to void are different. So you will require slightly different underlying softwares, but there everything gets installed every time. Of course, one of the downside here is that everything needs to be reinstalled every time. So it takes a couple of minutes to do that at every session. So sometimes you might get some errors here, for instance, with incompatibilities. So there you don't have to worry too much about those. at least that doesn't impact the way that the software works. But one thing that I wanted to point out here as well is that at the end of the install cell, one of the things that is being checked is whether the notebook is up to date. So we try to release a new version of the notebook to, of course, fix bugs and make new updates. And here is one of the ways that you can check whether the notebook you are using is the latest one. So if you want to save the notebook to your own Google Drive and keep a local copy, then of course you may not be using the latest version of the notebook. And here is where you can find out whether it's up to date or not. So something to keep an eye on if you are using the notebook. And so as for the noise to void, here we have a file called the requirement file, which is specific for Stardist, that if you want to use a notebook locally, then here you will contain the list of all the dependencies that you need to install, which can be useful if you want to either run it locally or install this on your own server. Okay, so is everyone up to the setting up the settings? So if I don't hear anything, then I will do like Romain did and assume that everything is going okay. So yeah, so you will see the setting cell is very similar to what you had with noise to void. Of course, now you're setting up a different deep learning network. So some of the settings might be different. So here in the text, we try to explain all of them. But if anything is unclear, then don't hesitate to reach out. But basically, the main difference that you have here between Stardist and noise to void is that they don't require the same type of data to train. So noise to void is actually a very unique network, is that it can learn from a single image by creating training patches from the same image. Stardist is not self-supervised. It requires to have one image of the images you want to segment and then the associated mask. So it's a supervised training. So you need to have a training source and a training target. So what do you start from and what do you want the network to learn? So that's what you have here. You need to have two folders where you indicate the location of both of those images. So here for me, they are in my Google Drive here. And then you should have in yours something that's similar than this, which is a Stardist, which is the data sets that we put in Zenodo. And then there, so some of the images that Romain was showing you at the very beginning of the workshop. And then you will have a folder called training, so training images, and then training masks. So the training images is what you start from. So those are your training source. And the training masks are what you want to achieve. So it's your training target. It's what you want the network to learn. So there, as for noise to void, you just indicate the location of those folders by right-clicking here and then copying the path. Okay. Then, as for noise to void, you need to indicate how you want to call your model and where you want to save it. So there, what I'm going to do here is to create a new folder that I'm going to call model to save my model. I'm going to copy the path and then put it here in model path. In terms of name, we're going to call it Stardist I2K. And then you can decide how many epoch you want to train Stardist with. And then that's pretty much it if you want to get started like this. But there's also quite a lot of advanced parameters that you might want to tune yourself if the default parameter don't work for you. So as for noise to void, you can control the batch size. Now you can see that the batch size is a lot smaller for Stardist because now actually the patch size that you want to use are quite big, which means that you can fit less of them in your GPU. Number of steps, patch size. So there was some question about patch size earlier. So in noise to void, it's good to keep the patch size small so that there is a lot of them. But for other networks, such as Stardist and CARE, the rule of thumb is to use as big of a patch size as possible so that it contains a lot of different examples in the same patch, but at the same time that the patch fits in the GPU RAM. So you need to be able to load those patches in the RAM for the network to be trained. So there it's good to use a very big pack size. And actually, by default, in the Stardist notebook, what the notebook is going to do is going to read the size of your image and then take that as a pack size, so load everything at once. But if your image is really, really big, then of course it might not fit in the GPU. So there you might want to tune the pack size in the advanced parameter.
Excuse me, Guillaume.
Sure.
Here it assumes that you have exactly the same number of images in the target and in the training folders, and that and how does it know which one goes with which one? It's just the alphabetical order?
So a very good question. So yes, so you need to have the same. So basically, in Stardist, you need to have all your images being annotated, and then your training images and the training mask need to have the same name, and that's how we can match.
Oh, the same name. Okay.
Yes.
And would it be possible when you run this module to be able to flick through the pairs? Because I see it only displays one pair, right? So
sure.
I'm not sure. I mean that because if you have a problem, for example, like there's a missing image, or what happens, or you have one that
if there's a missing image, you're going to get an error, basically.
At that stage, or when you're training?
Before training, you will get an error. Yeah, before the training starts. So if you have a missing image, or if one of the name is different, so let's say you have an extra space or something like this, which might happen, then you will also get an error before training.
No.
So you've already run the cell, which is great. So one of the things I was going to say here, and then Christophe, you can run it again, is so normally you will train Stardist for hundreds or maybe 200 epochs to get a really good model. But if we do that now with this training data sets, it's going to take at least 1 hour to 3 hours, depending on what GPU you've been allocated. So what we're going to do instead is we're going to train Stardist with only 10 epoch. And we're going to use transfer learning to speed up and improve the training process. And then if you want, later on, you can play with training Stardist from scratch with a much higher number of epoch as well. So if you've already run this cell with 100 epoch, I will suggest that you run it again with only 10 epoch. Here. And then here, yes, as Christophe said, so you only have one example that's being displayed. If you think that it would be useful to show more, it's something we can easily add as well. Okay, so is everyone okay with loading the data? Okay, so it sounds like everything is going okay. So here you also have the possibility to use data augmentation. So again, if you have a small training data set, you can use that here. So we can talk about that a little bit later when we use a Stardist model and how we go through annotation of data. But what I wanted to show you here is the use of transfer learning to use a pre-trained model to do transfer learning. So as we've said during the talk, and Romain was also explaining later on, is when you train a deep learning model from scratch, you set up all the weights, so all the settings inside of the model randomly. Which is, of course, absolutely not the best way of doing it, but it's the only way to do it if you don't know where to start. But if you have a good model that you know is performing well to start with, but you want to build up on that, then you can load the model here. So, of course, it needs to be a Stardist model by using a pre-trained model. And so in this cell, for instance, you can load pre-trained models that have been generated by the Stardist authors, so one which is really nice to segment nuclei, and that's the model you will find in Stardist Fiji plugin, for instance. You also can load others model here, but if you've generated your own Stardist model, you can also load it here from file. You can choose between whether you want to use the best weight or the last weight to continue the training. So here we can use the best, and you just run the cell. So if you use the 2D versatile Fluo model from the Stardist Fiji plugin, the first thing it's going to do is to download it so that you can have access to it here, and then to load it. And one of the things that happens here is that actually we do not know which learning rate was used to finish training this model. So instead of loading the latest training rates, we're going to use a default one to get started. So that's why you get a warning here. But if you were to train your own model, let's say for 100 epoch, but you wanted to reuse it, but train it on a slightly different data set, then there you will be able to reuse the latest learning rates that you've been using. Then once you've loaded the pre-trained model, you can create the model and dataset object, which basically generate the patches and match the images together. One thing that I also want to show you is that when you have a cell running, nothing stops you from pressing the next one, and the next one, and the next one. So it's an handy little trick that, for instance, if you have a very long training session, but you want some subsequent cells to run, but you're not in front of the computer, then you can let it run. Because Google Colab, of course, has several limitations. One of which is that if you have no activity in the background or in the web browser for at least half an hour or sometimes 20 minutes, then your session will be automatically disconnected so that the resources can be freed and be used for a different user. But here, if you wanted to, for instance, start the training session, but also have a look at the training curve later on, but at the same time, you know that the training will take 3 or 4 hours, and you want to go and do something else, like go on a microscope and take more images, then you can already preload the analysis you want to do. And they're just going to run one after the other. Okay, so now it's training. So depending on what GPU you have been allocated, your training may be either a little bit faster or slower than what's going on here. But so do you have any question up to now? And is everyone training started? Okay, so I don't hear anything. So again, don't hesitate to interrupt me if there's anything. But basically what you're seeing here is very similar to what you've seen before for noise to void. You can see that we're going to do 10 epochs, so 10 rounds of training. But now we have more images. And also the batch size is very small, which means that only 2 images are seen per step. So you also have more steps. That's why it's also taking a little bit longer. Okay, so while it's training, what I can show you is, actually, I'm going to open Fiji now, and then we're going to look at the Start This Fiji plugin. So let me open Fiji. Okay. So in the instruction for the workshops, and I was indicating a few update sites that would be useful for you to install, and one of it is Fiji. Fiji, of course, but one of it is the CSB Deep plugin and the Start This plugin. So a couple of things I wanted to show you. So the first one is you've seen in noise to void at the end of the training, the model is exported in a way that it can be used in Fiji. So if you wanted to do that, at the moment, the way to do it is to go to File, then to go into Imports, and to open what's called bioimaging.io.zip. So these things might change quite a lot in the future because the CSB Deep Fiji team is reorganizing a lot the ways that their plugin is working. But at the moment, one of the ways that you can load the model from here is using the command here. Another way to do it is to go into plugin and to go into the CSB Deep and then run your network. So the run your network function here is actually a little bit outdated, but still works quite nicely with the models that you can train in ZeroCost. Do not use a noise to void predict function here. So this one, it's not compatible yet. So that's something that as soon as they've released how to export a model to be used with a noise to void predict button, we will be able to add that to ZeroCost, but it's not available yet. So in case you want to generate model and use them in Fiji for noise to void or for care or for denoise seg, then I will either use run your network or in here in file, import, and then bioimage.iu.zip import. So that's one thing. If you want to use Stardist, then you can go into plugin, Stardist, and then start Stardist 2D. Yes, of course, I need to open an image. So let's open an image, which is one of our test image. Okay. Hopefully you can see the image as well, which is basically nuclei, and it's a little bit of a noisy image. Now I can go back, Stardist 2D. Okay, now it's working. So some of you have used this plugin before, and it's actually a really, really good plugin. It's something that we use in the lab often, and it's very useful. And one of the things that's really good about it is that they provide some excellent, already trained Stardist models that are often performing quite well to detect nuclei. So this one, which is called the versatile fluorescent nuclei model, is actually the same model that we are currently using to do transfer learning on. So you could already use that and see how it performs on your own data before you start using our zero-cost notebook if you wanted to use Stardist to see whether it's worth using that as a starting point for the training. So here you can choose what model. You can, of course, change your settings here, though it's not, the point here is not to show you exactly how all of that work, but basically what I want to show you is that here you can control the output type. You can choose whether the identify shape go to the ROI manager or to make a label image, or you can do both, and then you can just run it and click OK. So when you do this, so it takes a few minutes. So I'm on a CPU only, so my computer is not accelerated by any graphic card here. And then I get two outputs from the Stardist plugin. One, which is a list of region of interest in the ROI manager, and one, which is a labeled image. And if you click here in show all, then you can have a look at all the region of interest that have now been identified by the Stardist model as being nuclei. And then you can already see one big problem here. So one thing which is great is that most of my nuclei have been segmented quite nicely by the plugin. But the big problem here is that there are a lot of things that have also been segmented, which are not nuclei in that image. And the reason for that, and that's what I was also highlighting in the talk, is that basically the images that I have are a little bit noisy, and they are different enough from the training data set that has been used to train that model, so that that model, even though it's very similar and almost usable, it's not quite usable. And it's a perfect case example of where transfer learning can really help you. So basically, what you can do is that you can train a Stardist network here, for instance, in zero cost. So now the training now is completed. And once you've trained a model that works well with your data here, you can download it and apply it into Stardist. And I will show you how to do that in a second. How's it going on your end? Is your training also completed, or are you still waiting? Okay, so I can't hear anything, so I'm going to assume that hopefully the training is also done on your end. And one thing you might see in the training window here at the end of the last epoch is that you have a series of optimization. And that's the reason why is that at the end of the training, what happened is that the network is kind of looking at your data and trying to optimize the instant segmentation so that it can find the best thresholding options so that the instant segmentation works. You also have some text showing you that the model has not been exported, and then you can use it in the Stardist Fiji plugin. But of course, we can now evaluate the training, and the first thing you can do is to inspect the loss function as in for noise to void. And then you're probably going to see something like this. And then here, of course, the loss function doesn't look nice at all. And so there's several reasons for that. And the first one is that we've been training only for 10 epochs, so there's not much time for gathering data on how the model is evolving over time. And the other reason is because we've been using transfer learning. So we are already starting from a model state where the segmentation works already quite well. So there's not so much learning to do for the model. He only needs to learn a little bit from your data and to optimize using your data to improve. So that's why you also don't have a huge difference in the loss over time. So I think this also nicely illustrates the fact that there's only so much information you can get out of the training loss and validation loss. And that's why the next session, which is a 5.2 part, which is on QC, is really important to kind of really assess the performance of the network you just trained. And so is everyone in the quality control 5.2 step? Hopefully I haven't lost anyone. Okay. So basically what you can do in this step is that you can indicate to the notebook where you have a test dataset. And a test dataset should contain basically raw data and gone through data, so inputs and expected output. And what we will do here in the background is that we will generate a prediction from your inputs and then compare it to what the ground truth is and assess how well the network performs.
Excuse me, Guillaume, but how is that different from a validation data set during training?
So the validation data set is still part of the training data set. And it's actually, depending on the deep learning network, it's a slightly similar concept, yes. It's basically doing exactly the same thing. However, it's often extremely good practice to validate your training data set on something that's really not been seen at all by the deep learning network during training.
Okay.
To really ensure that you validate on something that's like as far away as possible as a training step, so that you know that you're not biasing yourself. There's no bias basically in any ways. Because some deep learning network can still use some of the results from the validation data during the training also to kind of tune themselves. And so there you're completely excluding those options.
Guillaume, can I just add something to what you've just said?
Yes, please.
So there's a subtlety. It's an important point, I think. There's a subtlety about validation with how we have presented it so far and how it can be used. Validation is obviously set aside and not used during the training. Sorry, not used as a training data set. But every time you're going to be coming back to the initial step of training and resetting a few more parameters and maybe retraining the model, you will slowly learn the features that are in your validation data set as well. So in the one session of training session, of course, your validation will never be seen, right? It will never be learned, I should say. But every time you go back and you tweak a few parameters and you start again, then somehow some of the validation data might seep into the training because you're optimizing to really get that validation loss minimal. So that's a way, that's what the field calls, data leakage in a way, because things kind of tend to leak. And that joins back to what Guillaume was saying. Then that highlights the necessity of having purely something that is really separated that will never ever be seen, even at the hyperparameter optimization stage, if that makes sense. Okay, so it's a bit more complex than what we're showing right here because we don't really have time to go through, testing lots of parameters and then going back and forth in this loop, slowly iterating over the training parameters to improve the model. But this is the idea behind validation dataset versus test dataset. I hope this helps a little bit.
I have a more practical question. You were mentioning that it's possible that your training would take hours and it logged you out after 30 minutes of inactivity. Is there something that we could set up that kind of sends a notification, like a microwave ding button that.
So yeah, sorry.
sorry?
So I think no, I was just going to say so. When you're training, it's not inactive.
Right. But when you're done.
But when you're done training, yes, then there it's set as inactive. But there, so if you want the next cells to kind of run already, so the best is just to set them. But when the training is done, even if you go and do something else and you get disconnected, remember everything is saved in your Google Drive, so you've not lost anything.
Okay, excellent.
Okay, so for the quality control data set, and you need to put your test data. So here for the StarDist, we have test image and test mask, which is an example of two images here, and then you can copy the path there. So one is the source and the other is the target. The target is what you want to achieve. And then you can run the cell.
Guillaume, sorry to interrupt you. Just wanted to let you know there's 20 minutes left, because we know that the session ends for everyone abruptly when the time is up. So just to let you know, there's about 20 minutes left.
Thanks. Here is what it will look like for the StarDist QC. So basically what it does is that you compare your inputs to your ground truth. And here is a StarDist prediction. You can see it looks quite nice already. And then you get one image as an overlay to show you what you may be missing. But at the same time, you also get a quantitative metrics to tell you how well is your segmentation working. So for instance, here it's displayed as a table. It's also saved in your model folder. And I will show you where to find that in a second. But you get a lot of different metrics that you can look over. And again, if you're interested in the metric, you can check them out in the ZeroCost paper, or you can look at it on our wiki, or you can also ask us if you want to. So you have both the display and the metrics telling you how is it going. And then you have things like how many objects have been detected as true positive, how many false negative. So for instance, here I've heard in the presentation today that some of you may be interested in using this kind of method to do countings, and you can very easily use StarDist to count how many cells or nuclei you have in the field of view. It's actually one of the outputs that is generated. So now if we go to the model folder that I saved, so you have the StarDist model we've just trained. As for noise to void, you get a lot of different things here. So the best weights, some configuration file. The model file here is what you can use to use in the Fiji StarDist plugin. And at first I wanted to show you, you have also the training report that you've seen also with noise to void. Now, because we've done quality control, there's another folder here called quality control, and then inside you have all those images that have been saved so that you can get an idea later on of what it looks like. You also have images of the training curves, everything is saved. And then as for the training, you also have a quality control report as a PDF, so I can download it here to show you what it looks like. Oh, I've opened the wrong one. So it's saved both as a CSV, so the metric is saved as a CSV, and you also have a report as a readable PDF. And basically there you have, in a readable format, basically everything we've seen so far. So the training curve, an example image of what the QC look like, and then a table with all the metrics that you have here. So which can be useful later on if you don't remember what the model looks like. And I would say as well, so because there's so many of you working in core facilities, if you want to provide training as a service, then it would be fairly easy for you to provide the model and say you can now use that in the StarDist Fiji plugin. And here is a training report, and here's a quality control report that goes with the model, as you would do, for instance, for mass spec data or this kind of things. Okay, so once you've generated the model, so as for noise to void, you can use the model directly here. So for StarDist, you can generate quite a few other things than just a denoise image, of course. There's quite a few different types of use. So here you can decide whether you want to analyze single images or if you want to image stacks. So stacks here would be time lapses, for instance. So for instance, that's maybe what we can do now. So here you have the test stack folder. You can put it here, and then you can choose where you want to save the results. So here I'm going to create a new folder here. I'm going to call it very imaginatively results. Okay, and I put it here. Then here I'm not going to analyze single images. What I want to do is to analyze stacks. And then you can choose what you want the notebook to save for you, whether you want the region of interest, which are saved in a zip file, so that you can later on analyze in Fiji, for instance, using the ROI manager, whether you want to have mask image, or whether you also want tracking file. So tracking file is something that we've added so that you can easily combine StarDist output, for instance, with TrackMate to do automated cell tracking in Fiji later on if you wanted to. So that's something that if you're interested in cell tracking or vesicle tracking, automated cell tracking, then it's something that might be useful for you to do. And then you can then run the cell, and now it's going to load the data, the stacks, and then go through them and save everything in your Google Drive folder. So there, each of the stacks have 86 images, so it's going to take a couple of minutes to go through them. But because we have only 15 minutes left, and I've promised you that I will show you data annotations, and I'm going to now go back to Fiji and to show you on how we annotate the data and how we use model train in ZeroCost to annotate data. So I'm going to go back to the models that we've just trained here. I'm going to download it. So that's the one called tf save model.zip, and it's going to slowly download. And basically, I would be able to load this in the StarDist Fiji plugin now to make prediction. Okay, so now it should be done. Okay, so I'm going to start with the same image. I'm going to go to plugin, StarDist 2D. And now, instead of starting from the versatile fluorescent nuclei, I'm going to use model from zip file.
C'est celui du...
Romain, would it be possible to mute? There's a bit of noise in the background. Do you think someone could mute that? Or... Thank you. So here you can choose where your model has been saved. So here now it's just in my downloads folder, which is this one that I've just created, and then you can open it. And then again, you can decide what kind of output you want to generate, and then press OK. Hopefully that works. Yes. And then now you can already see that basically by training using your own data, you get a segmentation that is much, much better compared to what you will have had using the pre-trained model. And that's because you've tuned the model using transfer learning to what you want to achieve, which is great.
I'm sorry, Guillaume, can you go over once? I was busy muting my screen and I didn't put the right. Of course. How do you find the, I mean, I used the zip that was downloaded, but I got an exception.
So you can go to model zip from the file, and then here in browse, you will need to find it.
Yeah. So I downloaded it. What is the file you use here?
So it's one called tf_saved model.
But because I downloaded the whole model folder from ZeroCost as a zip.
Oh, okay. So no, so that's not what you need. So there, the only file that you need to use it in StarDist is within the model folder. There's something called tf_save model.zip. So that's the only one.
That's the one I downloaded.
Yeah. So that's your model being exported so that it's compatible with the Fiji plugin.
I see. Okay, should work now. Thanks.
And then if you now click OK, and you have the right TensorFlow library and everything, then it should hopefully give you a nice segmentation image. Is that working for you now, Christophe?
It's looking a lot like the first one, so I don't know what happened. I have a lot of stuff on the right of the image.
Okay, so did you choose from the menu, from the StarDist plugin? Did you choose model from zip file?
So plugin StarDist 2D.
Yeah.
So model from zip file and tfstev model.zip. Okay. And I just click OK after that, right? Yeah, so it's really this exactly like the one that was, I guess, quite strange.
Oh, that's interesting. Is anyone else having the same problem?
You pre-trained model, Christophe, when you trained that one?
Go back. So.
Is anyone else stuck here?
Yeah,
as well?
use the pre-trained model to be versatile.
And you've ticked that box, right?
Yeah. It says the learning rate cannot be identified. So, and then create the model. So yeah, I did the 10 epochs. Then I have the.
Very strange. I'll be interested to know more about what happened there, Christophe.
You want my TF saved model?
Sure. Yeah. I'll be back in touch with you about that afterwards.
I'll check.
Is anyone having the same issue or?
Well, actually, so I made I run on a copy. So can I just pass you the whole notebook, or will this work with all the results and everything?
No,
you can. Yeah.
Yeah, but the notebooks will not contain the memory, the
okay.
data in memory, right? It'll contain only the code and what you filled into the inputs, not the. So
but I will share my model folder with everything that has been done during the training,
yes,
so you
please.
will be able to see what happens.
Yeah, thanks. I've never had that before, so that's why I'm quite interested to find out what the issue is, and then I can run your model as well to the same StarDist version that I'm using here to see whether it's a model problem or if it's a StarDist plugin problem.
I see.
So I can't hear anyone else saying they're having issues. So is that because everything went well, or because I've completely lost you, or?
No, there's some comments in the chat saying that at least Pierre has replied saying that that's fine for him. He's following along nicely.
Okay, cool. Thanks a lot, Pierre.
Sorry, Jennifer?
Oh, just saying mine looks
okay.
Well. The same results.
Yeah, I had to rerun some training steps because I renamed the model folder halfway through, so it gave me an error when we were in cell number 6. So.
Okay.
Excellent.
Okay, so we have maybe like 10 minutes left or so. So what I wanted to show you is what we do now, which is, I think, the most important in a way is the generation of training data sets, right? So the biggest problem with deep learning now, and I guess it's the last frontier in a way, is the annotation, and which is what takes the longest. And the way that we do it now in my lab, especially for StarDist, is that we use an iterative process. By this, I mean is that if you have a model that works okay, but not perfectly on your own data, then you use that model to generate the first training data set. And by that, I mean this. So if I go now to the plugin and I open StarDist again, and then I will use the versatile fluorescent model. And so now let's imagine that I don't have any training data at all for my images, and that's the best that I can get at the moment, which might be the case for some of you when you want to use StarDist to analyze your nuclei. But actually, this is really useful because if you have to draw all the nuclei here by hand, it will probably take you about 4 hours to label 10 images. Actually, that's generally how long it takes me to enumerate images manually. But now what you can do is just highlight everything here, and you can see that actually you don't need to annotate everything by hand, because the network's already done a really good job at annotating many of them. So what you need to do is just delete the ones that are not good. So then you can create better annotation. And then for that, you can use the magic wand and then just click on the annotations that are not good and just delete them, so that they're not in your ROI manager anymore, right? So of course, it's still going to take time to do the annotation, but it's not going to take you nearly as much time as it would take you to do it from scratch. So there, I'm not going to show all of it, but you get the idea that you can correct and all the misannotation. Then you can go carefully over the images to make sure that everything is good. So for instance, here, that little guy is not good. So here is dividing cells. There's really 2 nuclei, and this not been identified properly. So you can redraw it and then add it to the ROI manager. So for instance, you can use a T button, which is a shortcut for adding to the ROI manager. And so you get the idea. You can, using pre-trained models that are already available, vastly accelerate your annotation. And then once you have everything in the ROI manager in a way that you are happy with, so all your structures have been labeled, what you can do now is to use a plugin called Loki, which is super useful. So you can find it in plugin, Loki. You can, if it's not installed already for you, you can use it. You can install it as a update site and then click on ROI map. And then what the Loki plugin is doing is that it's going to take everything that you have in your ROI manager and is going to generate a new label map. And that label map is basically exactly what you need to train Stardist. So that's one of the ways that you can use to vastly accelerate the generation of training datasets. Now, you're going to tell me, okay, but what happens if there is no pre-trained model available to me to do this? Then what I normally do in the lab, so we use Stardist not only for fluorescent images, but also for bright field images. So what you can do is then you annotate 10 images by hand of cells, let's say, and then you do it in the same way. So you would, let's close this and I show you. Now I'm open this and I will draw manually to annotate it. And I'll add everything in the ROI manager. And then when everything is there, then I can use Loki to create a ROI map. And then I will only annotate, let's say, 10 images or 15 images, depending on how many structures you have in your image. Then I will use ZeroCost to train my first Stardist model with a very small data set. I will use Augmentation to increase it. And then I generate my first model. It's not going to be a great model, for sure, because your data set is small. But then you can use that model and the Stardist Fiji plugin to accelerate the annotation of more images. And it's a huge time saver because it might take you 10, maybe 10 hours to annotate 10, 20 images. Then you train a model, and then you can annotate another 50 images in another like 5 hours. So you can really speed up the generation of new annotated trained data using this kind of strategy. Does that make sense? Any question on this, on how you can use basically training a model with a small amount of images to kind of generate the first model and then use that to annotate more of your data and then carry on like this until you get basically a model that's as good as you need to do your segmentation. So if you're interested in this, we wrote a small protocol which contains a step-by-step like instruction on how to do this. So it's on the bioRxiv. It's also on the faculty of 1000, but you can find it here. It's in with I can show you the faculty of 1000 version. So it's a small protocol explaining how to connect StarDist and TrackMate, but within this protocol, there is explanation on how to really step-by-step train a new model using that iterative approach to save you a lot of time. So I can show you here. It's in the extended data. Yeah, and then here, if you're interested, we also provide several pre-trained StarDist models that work quite nicely for the segmentation of bright field images. So you could potentially think about whether, if you need to segment bright field images, start from those models to train your own. Extended data is here, and then we have a full protocol here as a PDF where you can have a step-by-step instruction on how to use this tool to annotate your data for StarDist.
Just 1 minute left, Guillaume.
Yeah, I saw that on the clock, so that's why I was kind of rushing a little bit. So I don't know if we're going to get disconnected again or not at the end, but yeah, so I hope you found the workshop useful. Thanks so much for coming. And if you have any questions, don't hesitate to ask them now, or carry on the discussion on Slack, or come and talk to us on Twitter.